this slope, but that slope is going to change depending on the other criteria that affect levels of power. So this is effect size D, that's very small, or smaller. This is, and then the orange line is effect size D, that's quite large. Point D of 0.4 is 0.4 standard deviations, because that's what effect size D is. It's the number of standard deviation. It's the, in standard deviation units, how much difference is there between two groups. And so in this case, the difference is 0.4 standard deviations, whatever the standard deviation is for any given case. And that line is, it's not flat, but my graph can't show the slope. Although if I got rid of these other ones and I added it, we could make it so it looked like it was sloped, but it doesn't look sloped because of really the other three that are on it. Does it make sense? So this is the more important takeaway, that as we increase alpha, we're going to increase our power. What, Cameron?
So if you're anticipating a large effect size, then you get to lower the sample?
All things being equal, that yes. But all things are rarely equal, right? But if they were, that yes, absolutely.
Because that line, your highest effect size, 0.4, was like, it just jumps
flat,
up immediately. Right? Yeah, it's like,
yeah.
Oh, we don't have to worry about anything here.
Yeah, and if I just had that line up there, I could make it look like it was sloped, but
Right.
if you put it on the same y-axis as the other ones, it just doesn't look like, it looks pretty flat. But it's not going to be, I can make it look sloped if I wanted to. But all of them will eventually start to flatten out, never again become flat, but continue to flatten out. All right? We're good? Questions? Michael?
Oh, just based on that graph, then is having like large effects size like a good way to still have high power, like and also still keep your alpha level low then? Or?
Yes, all other things being equal.
Right.
Sample size and the level that you set power at, that would be true. Does it make sense? Other questions? So alpha is one determinant of power. Another determinant of power is effect size, yeah? And so Cohen says someplace that, and do I have it up here somewhere? I don't think so, but Cohen says someplace, and I can find he says this thing that we call science, the enterprise or the endeavor of scientific discovery, is all about effect sizes. If it's about nothing else, it is about effect sizes. And agree or disagree with that. But to me, it does make some sense, because that, in some ways, that's really what, at the end of the day, not the only thing we care about, but it certainly is one of the things we care about. So all things being equal, ceteris paribus, power increases as effect size values increase, right? So same graph. No, I guess it's on the next page. You can flip a couple pages and see it. Same graph looks very similar. As we hold steady everything else and we increase our effect sizes, we're going to have that curve with diminishing returns as effect sizes get larger. And the reason why that's the case is smaller effect sizes are just more difficult to reliably detect with the statistical tests that we use. And so just a little brief primer on effect sizes. Effect sizes describe how large the relationship is between, in most cases, two variables. And in this case, I say explicitly two variables, but it could be, as we'll see later on, it could be a number greater than 2 as well, but at least 2 variables would be a better way to write that. Effect sizes, you can scribble that note in there and I'd feel better. Effect sizes describe how large the relationship is between at least 2 variables, and maybe more. Effect size is the degree to which the null is believed to be false. That's from Jacob Cohen. It assesses the amount of total variance in the dependent variable that is predictable by our knowledge of the levels of the independent variables. That's from at least my edition of the Tabachnik and Fidel textbook. And statistical significance examines the reliability of an association. Effect size is a measure of the magnitude of said association, okay? So the significance test is how reliably, out of 100 times or 1,000 times, how often are we likely to get these or similar results? That's what the statistical test of significance tells us. Effect sizes is a measure of the magnitude of the association. Which one of those two seem more important? Reliability or magnitude?
First one.
Huh?
First one.
Reliability is more important than magnitude? Why?
If our measurement is not reliable, how can we use the magnitude or
Yeah, good. So if it's not reliable, who gives a rip about the magnitude? Yeah. So what does everybody else think? Agree?
I don't know. I mean, maybe I'm wrong, but kind of my thought is like, if something really, really big happens and it only happens once, it can still be really important.
Sure. Good point. And I think fair point. The other point that I would make, I could add another 100 people to my sample and I'd change the probability, right? So I'd maybe go from being non-significant to, and if 100 want to do it, I could add 200, or if 200 want to do it, I could add 1,000, right? Because probability significance tests are, as we're talking about, one predicated on the sample size, right? Same isn't true with effect sizes. Will effect size change if we add 100 people to the sample? Is it going to stay exactly the same?
No.
Let's say we have a sample of 500 people, and we have a measure of effect size, and we add another 100 people to it. Are the two sample sizes from the original 500 and the new 600 going to be exactly the same? No, of course not. They're going to change, but there shouldn't be, if you have good data, there shouldn't be, we wouldn't be able to jump from conclusions significant or non-significant, which is like night and day, right? It's just going to be, it's going to go up a little bit or it's going to go down a little bit based on our greater sample size. And so, in some ways, to me, well, I think in many ways, to me, effect sizes are a better measure of what's going on with a set of phenomena that somebody's studying, because we can always change, we can just add more people or things, whatever we're studying, and we can change significant levels. Same isn't true with effect sizes. And so I think there's probably a decent argument to be made either way. So far, so good? Michael?
Could you say that the more people you add, the more accurate, theoretically, that your effect size is?
Sure, your ceteris paribus, your margins of error for the effect size are going to shrink as you add n to your study. Again, assuming everything else is held constant, which is a big assumption, right? We're good? Yeah? So a couple, and we'll talk a lot about R square when we talk about regression. Eta square partial eta square. D is, we looked at D a little bit ago, we'll talk not so much about D. D is just a measure of, in standard deviation units, how much difference there are between groups. But eta square, partial eta square, which I don't list here, and R square are three measures of effect size that we'll talk about a great deal as we move forward. And so in the Cohen article that you read for today, and these are three numbers that I hope we can remember. So small effect size is R square of about 0.01. And this is right from the Cohen article. Medium effect size is an R squared. This is R squared, not R. 0.09. And large is 0.25. So if you read a study and they report an R square of 0.085, what would you say? Would you say, oh, this isn't a very important study because it's a small effect? You better not say it's small. You better at least say it's medium, 0.085. And if it's 0.25, he considers large. And so it's useful. It's useful to keep in mind. And if you square these, 0.1, the square of 0.01 is 0.1, 0.3, and 0.5. Yeah. If you take the square root, did I say square? If you take the square root of 0.01, it's 0.1. Take the square root of 0.09, it's 0.3. Take the square root of 0.25, and it's 0.5. And so what Cohen says, and I really like, this is halfway in between here and here if we have taken the square root, right? They're not in square root or in squared terms, but if we take the square root, 0.1 and 0.3 and 0.5, this is right in the middle, right? 0.3 is 0.2 either direction. And so he picked these three effect sizes because he thought large, and you read this today, he thought large was what? From your reading today, he said large is fill in the blank with a maximum of 3 words. Brianna? He said, anybody got it? He said large is an effect that you'd easily be able to detect by observing the phenomena being studied. So it's something that you don't even have to be a careful. He says the middle size is a careful observer would be able to detect that level of relationship. And then this is one that you may not be able. There's not enough. There's probably enough noise and not enough signal to detect the signal, even perhaps for a careful observer. And so it may not be detectable in ways other than doing, empirical, very careful observation, measurement of what it is that we're studying. So to me, it makes perfect sense. The last point that I'll make, did I make all these points on the next slide? I pretty much cheat on. The only other point that I would make is this, that if we look at the communication discipline or social sciences writ large, and let's say we did a meta-analysis of every study that was ever done that reported an effect size. My guess is we're going to come up with an effect size that's pretty close to 0.3. R, not R squared, R of 0.3. With the standard deviation, that's going to be equal to probably about 0.2. And that makes, and if you read enough meta-analysis and you start noting what is being reported in terms of, it's never, there's always exceptions, but it seems to generally hold true that across a large body of studies, the average effect size of all of those studies is about 0.09. A standard deviation below that would be an R square of 0.01. A standard deviation above that would be something around 0.25. All right? Does it make sense? So, obviously, if we're changing effect sizes from, this is in the D metric, because that's all that G power lets me do, I think. I assume that's why I use D and not R or R squared. So a D, this would be an R square of 0.01, this would be an R square of 0.09, and this would be an R square of 0.25. And we can sort of see, although my graph isn't able to show this line, it looks like it's flat, right? But it, obviously, like with alpha, it never is. It never is flat. It's always sloped, but the slope diminishes as we approach 1. Does it make sense? Questions? No? Changing sample size and effect size. Good? Questions there? And then a third determinant of power would be sample size. As n increases, estimates become more precise. Example being, as our n increases, our margins of error decrease for standard error of the mean, for example. Because the formula for standard error of the mean is, anybody remember?
Sample mean minus
It's the mean divided by the square root of n. And so the standard error of the mean, decreases in size as n increases. And if you want to know in terms of the mean anyway, the decreases at square root is the level of decrease that would happen. So it's not a straight line, it's a curved line. Make sense? Yes? Same type of graph, just vary sample size from 50 to 1450, holding all of those things in the top constant, and we can see what happens to our statistical power. So we can talk about several different types of power analysis. Which one do we tend to do? Which one's most useful? The first one, the second one, the third one, or the fourth one? Post hoc? A priori? What do you think?
Priority.
A priori. Why?
Because, like you said, we don't waste resources if
Yeah.
we don't have anything to do.
Yeah.
I thought that post hoc was the most common.
Why do you think that? I don't. It might be. I don't know why it would be. It's not useful at all, though. The reason being is, if your test was significant, you're going to have power that is adequate. If your test was non-significant, regardless of how large your sample, you could have a sample size of 17,000. If your test was non-significant and you did a post hoc power test, it's going to be below 0.8. That's assuming you're using you're using the effect size for the test that you just did, not some effect size that you take from some. But if you use the effect size from your study, that would indeed be true. you would always find, if you had statistical significance and used the effect size that you had for your study, you'd be overpowered, or above 0.8. And if you didn't find significance, using that effect size for that study, it would absolutely be under 0.8, with some margin of error a little bit. Elena?
Dan, so I was wondering, because it says that you should be estimating the effect size when you're doing, like when you're trying to determine statistical power, but what if it's something that hasn't really been tested, or you're trying to like build a scale or something?
It's just that's the difficult part. That's why statistical power is not an exact point estimate. It's an approximation, because we don't know. If we knew exactly what the effect size would be, why are you doing the study, right?
Yeah.
And so we don't know what it's going to be, but we can use resources that we have available. For example, where could we find? Let's say it's not that situation, Elena. Let's say it's you're not treading brand new area. We can talk about that in just a minute. You're not tilling brand new soil. You're doing not a repeat of another study, but you're doing another inoculation study. But you're adding something onto that study. Where would be a good place to start in terms of what, besides asking Dr. Banis, where would be a good place to find an estimate of the effect size? Yeah, you could use the meta-analysis that John did a couple years ago as a good starting point. But still, is your study going to have that exact? No. And so the one thing that is always, I just find curious, I don't really ever say anything about it, but when somebody says they need a sample size of 147, and they're like just married to that number, that until it's 147, I'm not good, and it doesn't need to be 148, and it surely can't be 146. That's just sort of a, I don't know, misunderstanding might be too harsh, but it's not clearly having, what the ability of power analysis is, or what ability does that. And it's not a absolute. We're going to get a point estimate. That's going to be the end that you need, but there's going to be big margins, or maybe not always big, but margins of error around there. And so, how would you go about? Let's say it is a brand new area. Nobody else has ever studied this before. You're doing a study. What would you do? How would you estimate the effect size? Where would you start looking?
I would assume it's small, right?
Why would you assume that?
Well, I remember reading that. I can't remember which article. I think it was the Cohen article, but it can always be bigger. So if you'd rather underestimate than overestimate.
And waste your resources?
Right. Well,
Just saying.
I mean, yeah. If you.
Yeah. I think that I would do the same thing. I think a good point to start would be R of 0.3 or R square of 0.09 would be because we know that that's the and so if you have no other information, the mean is always a good place to guess, right? For any phenomenon, the mean is a good place. If you don't know anything else, that's a good place to guess. Are you going to be right on? Probably not. But if that's all you have, you lack any other information, that's a decent guess. And so you could take the mean as a starting point. I like the idea of maybe erring on the side of too small of an effect size and then maybe wasting some of your resources as opposed to, and it might be a bigger waste of resources if you estimate too large of an effect size, you do your study, you don't find any effect, and you end up having to stick the whole thing in a file drawer and never publish it, right? That's not proper utilization of resources either.
Doesn't increasing
No,
Are we good?
doesn't increasing the n say that the effect size is medium and you plan for a small effect size, so you oversampled a little
Yep.
bit. Doesn't increasing that n reduce the beta, or reduce the probability of a type 2 error? If you have more sample than you needed, does it decrease the probability of a type 2 error?
It will increase if you have, as you increase your sample size, you could increase the likelihood of making a type 1 error finding an effect that, because you have a sample size of 17,000, that's so small as to be practically of no significance. You know, it's the R is 0.00, the R squared is 0.0001, right? And if I have n of equals 17,000, I could find that. So I don't know if I don't think I answered your question.
I'm gonna think about it.
You
Isn't it
you
like
think
your
about it and
sample
then let me
size-
think about it too. But that would be my response, and hopefully I didn't confuse
Yeah.
the issue.
No, that makes sense. I mean, we, like in stats one, we pulled a huge data set. He's like, run this test. And it was something that there shouldn't be a difference between the two groups. But there was a statistically significant difference because we just had
I could generate 2 columns of just random data. N equals 17,000. I'll just keep going with that number, and I could correlate those two, and the p-value. I can't guarantee it, but I would bet a cup of coffee that it would be less than 0.05.
But does
But it might be sort of there's chance. It's just junk data, right? It's just 2 random vectors of data that you tell a computer to generate 17,000 random numbers between 0 and 1, and you correlate those two, and it's going to be, I think you'll find statistical significance. I'm going to do it tonight, and I'll let you know. But I would, a cup of coffee, I would be willing to say right now. Brianna, you had your hand up earlier?
I know I'm kind
No,
of wavering
no,
on
you're
that,
good.
but because based on his question and your answer, then what I gather is when we increase our n, we have a greater chance of a type 1 error, but not a lesser chance of a type 2.
That's correct.
Okay.
We're going
That
to
was my-
increase.
Yeah.
Yeah, and what we'll end up having, there's no free lunches. There's the trade-off that as you increase one, you're going to decrease the other, and decrease one, you're going to increase the other. And it might not be that you make, a type 1 error, but you might find effects that are so small as to be of no practical significance. Again, R squared is equal to 0.00001. Who really cares? That's pretty harsh, but it's just not all that. There's just not much going on there, and it wouldn't be going on if you didn't have n equal to, say, 17,000.
So we didn't, I know the larger your sample, the greater it's going to be significant. Is not necessarily a type 1 error because it's accurate measure of what's really going on. It just is so small.
If I generate 2 random vectors of data with 17,000 observations in each column and correlate those 2 columns, and I find a significant correlation, does that mean there's something going on? I guess there is. I mean,
But the
but
effect size is not
yeah. And so I've had that. It's sort of an interesting argument that you could have with your significant other or whoever. Can you ever have too much power? Is sort of what we're getting at. And okay, you find significant results. And some people, those of you that knew Dr. Pao, that was sort of a serial argument that he and I had. He thought, no, I mean, if you find it, so this is what we'd argue about at Wendy's when we had lunch. If you find it, then damn it, it's there. But my argument would be, well, so what? It's there. It doesn't mean anything. It's so small as to be not utterly useless, but it approaches. And so that was, and we did have the, and Dr. Miller would, you could go have the same argument with him, and I have, and he'd take Dr. Faust's position too. It just doesn't think you can't be overpowered. If there's something going on, there's something going on, regardless of how small it is. And I just don't think so.
But it sounds like the argument of what can we do with this information. So even if we do make the argument, yes, there's something going on, Yeah, but it's so small, what can we do with it? We can't do anything.
I can get it published because it's significant, right? I can do that
Okay, so.
because people don't look at effect. I could probably not even report the effect size and see what the review process. The review process is better today than it was 30 years ago.
Yeah.
I would. Most people wouldn't sort of let that fly. If I see n equals 10,000 and they're reporting significant results, and no effect sizes, it would be this can't be published until they report effect sizes. But what can we do with it in terms of bettering the
Yeah,
human
picture.
experience? Good luck. I'm not sure that there's a whole lot. So far, so good? Nobody is ready to take a nap yet? Is it warmer in here than, well, some people have their coat on, some people, I'm just like,
It's one.
huh?
It's one.
So how did we get from here to where we were? I'm not sure, but I'm gonna start sort of over here, but I don't think it's not gonna be a recapitulation of everything that we just went through. So power as a function of alpha, effect size, and n. So we do our study, we have our alpha, we have the effect size from the study, we have the n that we did in the study, we can calculate power, right? And that's what if you click the little box in SPSS, if you sort of mess around with, what do they call it in SPSS? When you go into dialog box for regression, for example, there's a little thing that you can click on, options maybe, or something similar to that. One of the things will be where you can ask for effect size. Is that under options? Or something similar. There's like a couple different things you click. One of them will be power analysis, and this is what it's going to give you. Not all that useful for the reasons that I gave earlier regarding those three numbers, okay? A priori is the most practical use of power as per your articles and as per your dissertation advisor or your thesis advisor, I'm sure. That's what they're going to be interested in. So we're calculating the sample size as a function of the effect size, the alpha, and power. And so alpha is sort of locked in for us, right? 0.05. Power is sort of we have a good number there. 0.8 is the number that we traditionally go with there. And so the only number, as was talked about, Elena mentioned it earlier, and we talked about it, is coming up with this number. And it's not it's as much art as it is science. Maybe more art than it is science. You have to come up with, and it's an estimate, right? You don't know exactly what you're going to get with your study. There's no way you know that, or you wouldn't be doing the study. Even if you're doing you're just replicating a study that you did last semester. Is your effect size going to be exactly the same this semester? No. Will it be close? I would hope so, but so we just don't know exactly what this is going to be. So we have to use our intuition, our resources to estimate what we think that number is going to be. And then the output would be how large of a sample that we're going to need. And that's what we're going to do. That's what the Cohen article does for us. And that's what we're going to do after a break. And that's what we're going to do with G-Power. A priori. Is this of much use? So we want to determine our effect size as a function of alpha, n, and power. What good would that be? Do we have much control over the effect size? Some, maybe. You can do a not very well designed experiment, and all things being equal, you probably have a smaller effect size. There's some other things that you could potentially do, but this isn't a very practical use of power, nor is this. And this isn't practical because the third one isn't practical because Adam, what's that?
Isn't that why you're testing? Like why you're doing the experiment?
Because you want to find out this?
Yeah.
Yeah. And so we just, and that is going to be what it's going to be. And it doesn't really, this is just not very intuitive at all. And if you understand power, it's sort of like, well, that just doesn't make sense why you'd want to do that. Same way with this one, right? Can we vary this much? A little bit, right? You could maybe say 0.1 and see if you can get away. Well, that's not the right word. See if you can get a public or whatever. But that is 0.05 is in most places going to be considered, and that would be sort of maybe not the ceiling, but pretty close to the ceiling. Other places you might be required to do something lower than that. So this one here, the intuition just isn't there either. But the one that makes the most sense, at least to me, is, and I think probably to you as well, is a priori. And so as I say, the most practical use of power is a priori, estimates of sample size given your study. And we've talked about all these. Too little power and the effect might be missed. Too much power might be wasted time, wasted resources. And effect size is so small as to be of little practical significance. And a couple, I should have another, so these are methods to increase power. 1, 2, 3, 4. Oh, I guess this, I do have a little, I didn't see the little purple thing there. So methods to increase power would be to use larger sample, improve the reliability of your measures. And we talked about how unreliable, meaning measurement reliability here, how low reliability tends to attenuate relationships between two variables, and meaning reduce relationships between two variables, meaning lower the effect size between the two variables. And so if we can increase that by improving our reliability, all things being equal, we're going to increase our power. Increase the strength of the treatment in an experimental design. Dr. Miller is really big on this one if you've ever worked with Claude. He wants to what's the, not the worst thing we can do that's not the right way, but how can we make this as strong, and it's a good argument. I mean, how can we make this as strong as possible within the ethical boundaries that we want to be constrained within? And so instead of maybe giving them the message 1 time, give them the message 8 times, or not a good example, but that would be something that maybe he would say 2 times or 3 times, and I've heard him say that before. Within participant designs, so same participants are studied at time 1 and at time 2, and less error when we do that, and therefore greater effect sizes. And so again, all things being equal, increased levels of power. And so after a break, we're going to work through the examples in the Cohen article, and then we're going to do the examples in the Cohen article with G-power, and then I'm going to have you do these problems with G-power and with Cohen's article when we get back. So let's take a break, and just 15 minutes, and we'll come back and we'll get started.